Hello dear students, a very good evening everyone. A very good evening everyone. Welcome once again to your favorite platform, that is the BYJU'S exam prep app. That is the BYJU'S exam prep YouTube channel. Okay. So quickly share the link of session and update all your friends that the session is now live, and let's get started. Okay, with the next important topic in this special 26 series, and today we are going to discuss the concepts and the questions from controllability and observability. Quick revision of controllability and observability to be taken in this session. Yes, very good evening all. Quickly keep joining. Just a moment. Yes. Okay ji. All right. So yes, controllability and observability. I hope you enjoyed yesterday's class, the full concept packed class, that is the Nyquist stability criteria. Okay. So, unlike other classes like where, we deal with questions and then do the revision. But in the Nyquist plot, I completely focused on the concept of Nyquist plot because I felt that students many a times are not clear about the concept area of Nyquist stability criteria, how that actually comes up. Okay. Chalo. Now, very good evening all. Good evening Akhil, Hari, Ashok, very good evening all. Okay, the intent for today's session is to have a quick revision of controllability and observability along with the problem practice, along with the shortcuts and techniques required. So let's get moving ahead. This is a regular introduction. Let's get moving ahead. And guys, as you know, UPSC Engineering Services results were out some time back, and BYJU'S exam prep students outshined once again. Okay, All India rank 1, All India rank 9, and 5 aspirants under rank 10, 29 under rank 50, and 37 under rank 100. Phenomenal results produced. Okay, now let us say I take a nth order control system. Okay, good evening Anubhav. Let us say I take a nth order control system, and of course, okay, if you have a nth order control system, it would definitely have n state variables, because the number of state variables of any system is equal to the order for the system. So let's say x1 to xn. Okay, let me properly arrange it rather. Let us say these x1 to xn are the n state variables for the nth order system. Okay. The system could be SISO or MIMO. Here I have considered the system to be SISO, that is single input, that is UT, and a single output, that is the YT. Yes, Akhil, definitely all revision marathons, including technical, including aptitude, and including maths, will be coming up in January. The January is going to be a power-packed marathon season for you. Okay. Okay, ji. Okay. Now, see, of course, guys, what state variables are, okay, why they are important, how do you define state variables, okay, how many state variables, okay, all that is a separate discussion point. So I'm not covering that today, otherwise we'll not be able to cover controllability and observability. Today I am taking a specific area from state space analysis, that is controllability and observability, because okay, again, there is a good chance of getting the question from here. This special 26, okay, targeting 26 most expected type, of topics from where questions can be coming up in the upcoming GATE exam. So I'm specifically touching the controllability and observability. And the next area that I'm going to touch in the next class would be the solution of state space model, where the concepts related with the state transition matrix will come. That is again very important. Okay. So, definitely we'll have just a basic assumption that you know the basics of state space model, what state variables are, how a state model is written, and all those things. Okay. Now, what is meant by controlling a system? When is a system controllable? A system is controllable if you are able to control the entire state of the system. Okay, the entire state of the system is defined by the state variables x1 to xn. Okay, so if you are able to control each and every state variable, how you can control? What is there in the user's hand? A user, okay, will have the input in the hand. Okay, so by applying or modifying the input, if you are able to control all the state of the system, all the state variables of the system, such a system is said to be controllable. Okay, now we talk about observability. So what is the point of observability? Okay, observability means observing the internals of system at any point of time, what is happening inside the system, and you can know anything about the system if you know the state variables of the system. That is why state variables are always important. Okay, if you have the knowledge of all the state variables, you have the entire knowledge, because the basic idea of state variables is state variables are those parameters, state variables are those variables of the system which will completely characterize the system, which can tell you the state of the system at every possible value of the time. Okay, so if I want to observe what is currently happening inside my system, inside my plant, okay, I would like to observe my state variables. And how do you observe? What is again there in the user's hand? User can check the output. Okay, and if by the measurement of output, the user is able to get the knowledge of all state variables, not only one, not only two, but by the knowledge of output, by the measurement of output, if the user is able to get the knowledge of all states, then the user is able to get the knowledge of the entire system, whatever is currently functioning inside the system, and such a system is said to be observable. That means you can observe the system at any particular point of time by measurement of the output. Okay, so these are the basic laws, these are the basic definitions. Quickly we are revising up. Okay, so the system is controllable if all the state variables can be controlled. Okay, if all the state variables can be controlled, okay, to reach a specific value. How? Okay, by applying the input, by modifying the input. All the state variables should be controlled. That means the entire system is controlled, because the entire system itself is defined by the state variables. Okay, even if there is a single state variable which is not in your control, the system is said to be uncontrollable. Okay, the system is said to be uncontrollable. Okay. Similarly, a system is said to be observable, जैसा मैंने बोला, if all the state variables of the system can be observed. How? By measuring the output. If you are able to observe all the state variables, then the system is said to be observable. Okay, ji? Right, Manjit, if you have any doubts, although the session is today in English, but if you have any doubts, मैं आपको please समझा दूंगा. तो कोई doubts है मंजीत तो आप बोलते रहिए. ठीक है जी. Now, what are the tests of controllability and observability? Let us come. As I'm telling you, let's have a quick revision. Okay, and then question practice. Okay, so this session is more about revision of controllability and observability. Okay, so Kalman's test of controllability and observability, most general test is the Kalman's test. After that, there is one more special test, that is the Gilbert's test. Okay, applied to specific forms only. Okay, but yeah, Kalman's test, the most general test to check controllability and observability. Okay, so suppose you have the state space model defined by, okay, so you know, whenever I talk about state space model, it always has two parts: state equations, which is x dot is equal to ax plus bu. Okay, and the next part in any model is the output equation. Okay, and that is y is equal to cx plus du. Okay, where u is the input, y is the output, x is the state vector. Okay, when I say x here means xt. Okay, and that is a state vector containing all the states of the system, containing all the state variables of the system, that is x1 to xn. Okay, that is the n cross 1 state vector of the system. X dot is the derivative of the state vector. Okay, the state space model is always divided into two parts: state equation and the output equation. Okay, now suppose you are given the state equation x dot equal to ax plus bu and the output equation y equal to cx plus du. Okay, acha, by the way, what is the size of all the matrices? ये तो मैंने x का matrix बोला. Okay, suppose I write down x dot is equal to ax plus bu. Okay, the matrix A is the system matrix of the size n cross n. Okay, the matrix X, the X is basically the state vector, a column vector containing all the states, and that is of the size n cross 1. Okay, now if you want to assume SISO, then U is a single input. But if I want to assume MIMO, okay, in case of MIMO, multiple input, multiple output, okay, we call U as a input vector. Okay, as an input vector of the size P cross 1. That is a P cross 1 input vector. What is this input vector? Suppose a system is applied by multiple inputs. Okay, so all the multiple inputs U1, U2, etc. are arranged arranged in the column vector, and that is known as the input vector. And suppose there are p inputs, I'm considering p inputs applied to the system. Okay, p is the number of inputs that is applied to the system. Okay, and then the size of the matrix B is then given by n cross p. Okay, similarly the output equation is y equal to cx plus du. Okay, cx plus du, where x is the state vector of the size n cross 1. Okay, now I'm assuming multiple input as well as multiple outputs. So if the system has multiple outputs, okay, we define the output vector again as a column vector containing all outputs. And suppose the system has q outputs, so there will be a column vector of the size q cross 1, where q is the number of outputs. The system has q outputs. The system has what? The system has q outputs coming up. The system has q outputs coming up. Okay, so q is a output vector of the size q cross 1. C is then the matrix of the size q cross n. Okay, u is again the input vector that is of the size p cross 1, and d is having the size that is known as q cross p. Okay. Now coming to the Kalman's test of controllability and observability, the first Kalman's test of controllability, a system is controllable. A system is controllable if the following controllability matrix has rank n. Okay, if the following controllability matrix has rank n and the controllability matrix is given by b, ab, a square b, etc, 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 up to a power n minus 1 into b. Okay, up to etc, up to the a raised to the power n minus 1 into b. Okay, that is known as the controllability matrix. Achha, by the way, what is going to be the size of this matrix? See, as I have mentioned here, okay, let me rewrite once again clearly. Yahi pe specify karte hain. What is the size of the B as I just explained you? B is of the size n cross p. What about AB? Look into AB. A is of the size n cross n. B is of the size n cross p. Okay, so what is the resultant matrix size? Okay, AB can be multiplied. Yes, the number of columns of first equal to number of rows of second. So yes, they can be multiplied. And then what is the final result after multiplication? That will be n cross p. So even AB, that will be n cross p. Similarly, you take the size of a square b, that will also come to be n cross p. Okay, all of this up to the a power n minus 1 b will be having the size n cross p, and all of these matrices are augmented together, means all of these matrices are combined together in a single matrix that is known as the controllability matrix S. Okay, so what is the size of this overall matrix? What should be the size of overall matrix? Okay, you are arranging one after the other towards the right. Okay, so what is increasing? You are not going up and down, the rows are fixed, but you are going towards right. What is increasing? Okay, columns. Each of them has n rows. Each of them has n rows. Okay, so the total number of rows is n, but p columns, again p columns, again p columns, p columns, p columns, p columns. So number of rows to n hai, but how many times p? N times p. Okay, so number of columns will be np. Number of columns will be np. Okay, so matrix S is having the size n cross np, but if I again turn back to SISO system, if I again turn back to SISO system, so SISO system mein, okay, we know that p equal to 1. What is p? Number of inputs. P is the number of inputs. So if I take p equal to 1, okay, the result will be n cross n matrix. N cross n bole to square matrix. N cross n bole to square matrix. Okay. Now, for a square matrix to have rank equal to n, for a n cross n square matrix to have full rank, okay, to have full rank, okay, rank equal to n ka matlab hua full rank, because a n cross n matrix can have maximum rank equal to n. A n cross n matrix can have maximum rank that is equal to n. So for the rank to be full, okay, for the rank to be full, okay, for a square matrix to have the rank n, what is only important is determinant not equal to 0. Whose determinant? Sorry, determinant of S. What is only required is determinant of S not equal to 0. I hope you know this from basic mathematics. For a square matrix n cross n to have rank n, its determinant should be non-zero. For a square matrix to have full rank, it should have non-zero determinant. Okay, or you can, watch my sessions on rank in the engineering mathematics. Okay, for a square matrix to have full rank, its determinant must be non-zero. Okay, yeah, that is what is concluded actually. So if you specifically talk about SISO, okay, what you only need is for controllability. Okay, what you only need is for controllability mod s not equal to 0. That means the controllability matrix should be non-singular. Non-singular means having non-zero determinant. Okay, having the non-zero determinant. So for a SISO system to be controllable, the controllability matrix should be the non-singular. Should be the non-singular. Okay. Chalo. Next, observability. Let us summarize both the tests together, then questions and shortcut pe jate. Okay, the system will be observable if the following observability matrix has rank n. Okay, so observability matrix, okay, V, which starts with C, then CA, then CA square. Acha, what is the size of C? As we have learned, the size of C is given by Q cross N. The size of C is given by Q cross N. What about the size of CA? What about the size of CA? C is Q cross N, A is N cross N, N or N ho gaya match. Okay, so the final order of multiplication is Q cross N. Okay. So when C and A are multiplied, the final size is again Q cross N. Similarly, if you try for CA square, same size you will get. So all of this will be terms Q cross N, and I am arranging all these matrices. I am augmenting all the matrices in a single matrix V. Okay, and I am arranging one below the another. Means if I am going down, 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 what is increasing? Number of rows. Okay, number of rows. How many rows? Q, 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 Q. Okay, so total number of rows will be NQ, because Q plus Q plus Q plus Q n times NQ multiplied by rows is fixed. Each of them has n rows. Okay, and I am not going right or left. The number of rows will be fixed, and that is equal to n rows, NQ cross n. Okay, so this observability matrix is having the size NQ cross N, where Q is the number of outputs. So again, if you come to SIS, okay, single output, single input, single output. So if there is single output, Q will be 1. Okay, and again, V will be a N cross N matrix, which is again a square matrix. Okay, so once again, dear, for full rank, for a square matrix to have full rank, its determinant must be non-zero. Its determinant must be non-zero. Its determinant must be non-zero. Okay, its determinant must be non-zero. Okay, so yes, for SISO system, okay, sorry, Q equal to 1 hoga. Okay, so for the matrix to have rank, for the rank V to N, for the matrix to have rank N, its determinant must be non-zero. That means the observability matrix should also be non-singular. Should also be non-singular. Now let's apply this on a problem. Okay, let's apply this on a problem. x1 dot is equal to x1 plus x2 plus u, and x2 dot is equal to minus x2, and y is equal to x1. And y is equal to x1. Okay. Now first of all, पहले तो इसको मैट्रिक्स फॉर्म में कन्वर्ट कर लें. Okay. If you want to convert this into the matrix form, x1 dot and x2 dot will be equal to how much? Okay, we need to write down this now. X dot equal to ax plus bu, where x is the state vector. Here matrix A will come, here matrix D will come. X dot is ax plus bu. What are the elements inside A and B? That depends on the coefficient. Okay, so what is the first equation? X1 dot is x1 plus x2. Okay, so what is the coefficient of x1, x2? Both are 1. So first row should be 1, 1. That is how you multiply row and column. Now 1 into x1 plus 1 into x2. Okay, plus how many times u? Plus 1 into u. So here 1 will come. Similarly, second equation, x2 dot, all second rows will come now. X2 dot is minus x2, only minus x2. Where is x1? Absent. Absent means take the coefficient 0. Okay, and minus x2, the coefficient minus 1. So now you multiply 0 into x1 minus 1 into x2. You get the x2 dot plus how many times input? There is no input term here, so 0 into u. so coefficient is 0. If a particular term is missing, that means its coefficient is 0. Simple. Okay, and then what about y? Y is only equal to x1, so we need to write down y is equal to cx, okay, plus du. Okay, y equal to cx. Okay, what are the coefficients of x1, x2? It is only x1, x2 is absent. Okay, plus du. Okay, d0 hai. Okay, the 1 0 x1 x2 plus 0 into u. Okay, so now you have all the matrices with you to start applying the test. Okay, this is your A matrix, this is the B matrix, and this is the C matrix. Anyways, D matrix is not required in the Kalmans, but now first let me start with the controllability test. Okay, for controllability test, what you need? First you need the controllability matrix S, that is written as B, AB, A square B, up to A power n minus 1 into B. But what is the size of the matrix? What is the system order here? 2. Na? There are only 2 state variables, so n ka value 2 hai. Okay, so if specifically you take n equal to 2, then the S matrix is very simple. Okay, because A power n minus 1, n is 2, so A power n minus 1 will be just A. So you have only 2 terms, B, AB, only up to AB. Only up to the AB. Okay? Now, what is the matrix B and what is the matrix AB? Dekho, B to given hi hai. So what is the matrix AB? Have a look into this. A matrix 1 1 0 minus 1. Ye copy kar diya. Multiplied by the B matrix. B matrix is this 1 0. Now multiply. Okay, first row, first column. The 1 into 1 plus 1 into 0. 1 aa gaya. Then second row with column. 0 into 1 minus 1 into 0. So that is simply 0. Okay, dear. So what is the matrix S then? It is B and AB. What is B? B is 1 0. AB also comes to be 1 0. AB bhi kitna aaya? 1 0. Okay. Now, what is the determinant of this matrix? Actually, what we need is the determinant. Okay, 0 minus 0. The determinant comes to be 0 and the system is not controllable. This is what is the Kalman's test. The system is uncontrollable. Okay. The determinant of S equal to 0 and I can say that the system is uncontrollable. Okay, the system is uncontrollable. ठीक है, clear है? Okay, chalo, let's move ahead. Okay, this particular system is uncontrollable and now let's move ahead. Okay, now let's take the observability. Okay, let us check the observability. Okay, for observability, I need the matrix V, which is C, CA, etc. up to CA power n minus 1. Okay, but again, if you take n equal to 2, so the matrix C will only be equal to C and CA power n minus 1 will be CA only. Okay, n का value 2 है तो A power 1 तक जाएंगे. Okay जी, ठीक है, तो I only need 2 terms C and C, out of which C is known to be. Good evening Ashok. Okay, C, this is the C matrix 1 0. Okay, multiply by A also. So let me find out CA. So C is this 1 0. Matrix A is 1 1 0 minus 1. 1 1 0 minus 1. So what this is equal to? 1 into 1 plus 0, that is 1. 1 into 1, that's 0. This is also 1. Okay, so what is the matrix V now, dear? That is C, CA. So what is the C matrix? 1 0. CA matrix 1 1. Now you have to calculate the determinant of this. What is the determinant? Cross multiply 1 minus 0. The determinant is 1, eventually non-zero. You have a non-zero determinant and I can say that the system is hence observable. Right? And the system is observable. ठीक है जी? Okay. The system is hence observable. So these are the fundamental procedures to test controllability and observability. ठीक है? अब देखो यहाँ पे next question. x1 dot is equal to x2. Okay, let me first write this in the matrix form. Okay, x1 dot x2 dot combined together in the column vector just like the previous case. Let me first write this in the matrix form. Okay, right, x dot is ax plus bu. Now first equation, x1 dot is only x2, x1 is absent, coefficient 0. Okay, okay, plus how many times u? There is no u, there is no input term, so input coefficient 0. Now x2 dot, second row, second equation. Okay, minus 2x1 minus 3x2, minus 2x1 minus 3x2 plus 1 into u, so input coefficient 1. Clear everybody? Okay, y equal to only x1, y equal to only x1, so x1 is 1, x2 coefficient 0, so 1 0 x1 x2, and again no input term. Anybody by chance know what special form is this? So as I'm telling you, today in this class we are focusing on observability and controllability methods and solutions. Okay, not the entire state space analysis. Entire state space analysis of course takes time, but if you have learned about the state space model, the standard important state space model, okay, there are some standard and important state space model. Okay, can you tell me what type of model is this? Anybody? What standard state space model is this? A very famous state space model. Okay, x dot is ax, a matrix A is 0 1 minus a naught minus a1, okay, plus 0 bu, y equal to c naught c1x. Okay, anybody? Yes, Kunal has got it correct. Yes, basically this is what is the CCF model. Okay, CCF model, and CCF is known as controllable canonical form, and controllable canonical form is named as controllable canonical form because it is always controllable. Abhi prove bhi kar denge. Okay, but whenever such question comes in the exam, if you see directly a CCF model, 100% close your eyes and say it is always controllable. Don't waste your time applying Kalman's test. Yes, Kunal, Ajay, Misaka, Ashok. Yes, it is the CCF form, controllable canonical form. Blindly you say it is controllable. No need to check, no need to apply Kalman's test. We will apply and still verify. Okay, but before I apply Kalman's, I want to take you towards the quick review, okay, of the CCF model. Okay, suppose there is a transfer function of the kind. Second order ki baat kar raha hu main. And then I will help you with third order. Okay, this is a quick review. Okay, we are not studying state space model today, but just 2-3 minutes let us review. So suppose you are given the transfer function for a system y by u equal to b c1s plus c naught upon s square plus a1s plus a naught. The CCF form is given by x dot is ax plus bu, where a matrix will be 0, the first row will be 0 1, and next minus a naught minus a1. See, what is a naught a1? Okay, that is the coefficient of the denominator starting from the constant. Reverse mein chalenge. Okay, a naught a1 with the opposite sign. Okay, a naught a1 with the opposite sign. Okay, plus 0 bu. What is b? If there is some common term in the numerator. Y equal to c naught c1x. What is c naught c1? C naught c1 coming from the numerator coefficient and starting with the constant first. C naught and then coefficient of s. थोड़ा और example से समझाते हैं. Okay, थोड़ा और example से इसको समझाते हैं. Okay, before I go to third order, understand one example here. Okay, suppose, okay, I give you a transfer function, okay, maybe that is of the form 3s plus 6 upon s square plus 2s, okay, plus 7, something of this kind. Okay, so this can be written as 3s plus 6. If you want, you can take 3 common. Okay, then s plus 2 divided by s square plus 2s plus 7. If you want to write down the CCF state space model for this, dear, that is written as x dot is equal to ax plus bu, y equal to cx only. There is no d here. Okay, now in the matrix A also, the first row is 0 1. In the matrix A also, the first row is 0, 1. Second row I told you minus A0 minus A1. Okay, the coefficient of denominator always start with the constant 7 and then go reverse 2, but both are of opposite side. So minus 7 minus 2. Okay, plus 0 BU. Okay, that is 0 and 3. Okay, 0 and 3. Ye ho gaya 3. 0 and 3. That is 0 and 3. Clear everybody? That is 0 and 3. Okay, 0, 3, U. Okay, B, the common constant. Y equal to C naught C1. Now what is C naught? Okay, look into the numerator constant, that is 2. And then next coefficient is 1 into S. So I'll write 1. Same sign. Okay, C naught C1. This is how you write CCF. Acha, for the same system, if you want to write down OCF, dear, for the same system, if you want to write down OCF, so dekho, no need to remember this form separately. Just one thing you remember, OCF is observable canonical form. It will be always observable. Okay, and how to write down the OCF? Just remember these points. Okay, the matrix A of OCF is the transpose of this matrix. Okay, the row becomes column 0, 1. Second row becomes second column minus A0 minus A1. Okay, the matrix B transpose will go to the C place. The matrix C taking transpose will go to the B. तो B and C को transpose लेके swap कर देना है. Okay, so let me write down. For the same example, let me write down the OCF. Okay, let me write down the OCF for the same example. तो देखेंगे यहाँ पे. Okay, so what is X dot? A matrix. Dear, take the transpose of this. So first row becomes first column. Second row minus 7 minus 2 is the second column now. Okay, plus. Take the transpose of C, that will come to B. Okay, so 2, 1, that is the row. Take the transpose, it becomes the column. So 2, 1 into U. Y. B transpose will come to the C position. Okay, the B is 0, 3. Take the transpose, it becomes the column 0, 3. It comes here. Y equal to CX. ठीक है? चलो. Similarly, you can have, okay, the CCF form for the third order as well. Okay, because I'm going to tell you some tricks around CCF and OCF, that is why I'm revising the form. Okay, that is why I'm revising the form. So ये देखिए CCF. Okay, so suppose there is a third order system now given to you. Okay, where y by u is equal to b, c2s square plus c1s plus c0 divided by sq plus a2s square plus a1s plus a0. Okay, sq plus a2s square plus a1s plus a0, and that is b c2s square plus c1s plus c0. Okay. Okay, now have a look into it. X dot is ax plus bu. Look into the last row. Again, last row ka pattern dekho, it starts with a0. That is the constant of the denominator. a0, a1, a2. Reverse chelenge, starting with the constant, but opposite sign. Same pattern. Okay. Then, what about the above? Dekho, second order mein it is 0, 1. For higher order, what you do? Last row ko exclude karke go above. Exclude the last row. Okay. Last row ko hata denge. Okay. Now, separate the first column. First column is all 0. And second column, like here, second element was second element was 1, unity. Here you should write down unity matrix. What is unity matrix? Identity matrix. What is unity matrix? That is identity matrix. Okay, 2 cross 2 identity matrix. तो ये pattern मैं आपको बता देता हूँ यहाँ पे. This is a 2 cross 2 identity matrix. So if I separate this here, the first column is all zeros. Okay, and what is this? This is the identity unity matrix. Okay, plus bu. B has the same pattern, only b 0 0 b. B is common of the numerator. Y equal to again the coefficients of the numerator. C0 again starting with the constant and then reverse C0 C1 C2, same sign. C0 C1 C2 with the same sign. Okay, so again, if I want to take an example here, suppose I give you some transfer function of the system as, say, s plus 3 upon s cube plus 5s square plus 8s plus 11, something of this kind, randomly. Okay, what is the CCF answer corresponding to it? What is the CCF model corresponding to it? X dot is equal to AX, third order hai, so 3 cross 3 matrix will come, plus BU, Y equal to the CX. Y equal to the CX. अब देखो, X dot is AX. Last row से start करेंगे. That will start with the constant. of the denominator. 11, then reverse 8, and then 5. All are of opposite sign. So minus 11, minus 8, minus 5. Okay. Then first column, ऊपर जाएंगे तो first column zeros, and here what you will write, 2 cross 2 identity matrix. Finish. Okay. B matrix 0 0 B. B means, is there any common? No. This can only be written as 1 into S plus 3. Okay, so if there is any common, there is only 1. I can call it as 1. Okay, y equal to Cx, C0, C1, C2, C0. Okay, the constant term of the numerator, 3. Okay, here there is no sign change, directly 3. Then next 1. Next, there is no coefficient of S square, so next 0. If a term is missing, the coefficient is 0. So this is the CCF model. OCF, you can write on your own. I told you the transpose technique. Okay. So this is a quick review, dear, about the CCF and OCF, and I was trying to tell you in this question that CCF model is always controllable. चलो एक बार check कर लेते हैं. Okay, it is always controllable. Let's have a quick check about this. Okay, so यहाँ पे देखेंगे, इसको यहीं देख लेते हैं. Let's have a quick checking of this. So we need the matrix B and AB. What is the AB matrix? देखो 0 1 minus 2 minus 3 multiplied by the B matrix, which is 0 1. देखेंगे 0 and 1, 0 plus 1, first element is 1, then 0 and minus 3. So what is the S matrix, dear? For second order system, we only need two terms, B and AB. Okay, B has 0 1, AB have 1 minus 3. Now check the determinant. Cross multiply is 0, then minus 1, and the determinant is minus 1, not equal to 0. That means it is controllable. What I'm trying to tell you is that if you identify it is a CCF model, you don't have to check any of these calculations. You can blindly say the system is controllable, 100% sure. That is how the system has got the name controllable canonical form. ठीक है, तो it is always controllable. ध्यान रखना, it is always controllable. चलिए जी, next. Okay, whether it is observable. Okay. What is the observability trick for a CCF model? वो बताऊंगा, but first let us prove. First let us check the observability. Okay. So for observability matrix, of course we need the CA matrix, correct? We need the CA matrix. What is the C matrix here? 1 0. What is the C matrix here? 1 0. What is the A matrix here? 0 1, minus 2 minus 3. Okay, so 1 into 0, 0 into minus 2, ये हो गया 0. Then 1 into 1, 0 into minus 3. That is only 1. Okay, so what is the observability matrix? Observability matrix is CCA. Okay, what is C? 1 0. What is CA? 0 1. Determinant not equal to 0. क्योंकि determinant आ गया ना. Cross multiply 1 minus 0. Determinant is 1, not equal to 0, and hence the system is observable. This system is observable also. ठीक है. Now, please pay attention. Observability का trick क्या है? Please pay attention here. Let me write down the transfer function of this system. Okay. Can I write down the transfer function of this system? चलो यहीं पे लिख लेते हैं. Okay, so see, we know that for second order, this is minus A0, minus A1. Okay, this is corresponding to B, and this is C0, C1. Okay, so what is the transfer function, dear? What is the transfer function here? B is equal to 1. Okay, C0 is the constant term, C1 is the coefficient of S. So how much? 0 into S. What is the coefficient of S? ध्यान देना, 0. 0 into S plus C0, that is 1, divided by S square. See, what is A0? A0 is 2 and A0 is the constant term. वो last में आएगा. Okay, then plus reverse चलेंगे 3S. Opposite sign, okay? Plus 3S plus S square. Okay, that is Y by U. So dear, what is Y by U? What is Y by U? Okay, that is turning out to be 0 into S is 0. So only 1 upon S square plus 3S plus 2. 1 upon S square plus 3S plus 2. 1 upon S plus 1, S plus 2. This can be factorized. 1 plus 2 is 3, 1 into 2 is 2. So I have broken it into S plus 1, S plus 2. The result is observable. How the technique is there, how the trick is there, before I tell you the trick, let me take one more example and then I will come back and explain you the trick. ठीक है, ये CCF explain कर दिया, okay, second order, third order both explained. Now let's come to the next question here. Then we will conclude the trick. Okay. So what is this question? Again, first write down in the matrix form. Okay. Again, dear, first write down in the matrix form. X1 dot X2 dot is equal to AX. X dot is AX plus BU. Okay, so what is the coefficient of X1, X2? X1 0, X2 1. Second row, minus 2x1 minus 3x2. Okay, input first 0, second mein 1 into u. Output equation y equal to Cx. Y equal to Cx. Okay, coefficient of x1, x2 both 1. 1 into x1, 1 into x2. So both are 1. Both are equal to the 1. Okay, so 1, 1, x1, x2. Okay, chalo. Now, dear, is this again the CCF model? Please tell me. Look into it, dear. 0, 1, minus A0 minus A1 plus 0 BU. Y equal to C0 C1. Perfect, perfect, perfect. This is CCF. So now, dear, tell me, should I check? Should I by chance check controllability? Do I need to check controllability? If you are doing that is a waste of time. CCF always is controllable, so no need to check. So the system is controllable. Now what about observability? Okay, observability ke liye, as I told you, I can again apply this procedure. Like previous question was CCF, again controllable, but for observability I applied the Kalman's test. One more thing we can do for observability now. Okay, yeah, let's come to this question. One more thing we can do for observability now. Yeah, let's come to this question. And what is that one more thing? Dear, again write down the transfer function. Dekhiye, this is minus A0 minus A1, this is B, and this is C0, this is C1. So what is the transfer function? Okay, numerator B common is 1, C0, C1 both are 1. So C1 is 1, 1 into S plus 1, C0 is 1. Divided by, come to the denominator, this is A0. A0 is 2, and opposite sign. Okay, then plus, reverse chalenge 3S plus S square. Okay, so dear, what is Y by U? Y by U this time is 1 into S, that is S, plus 1, okay, divided by S square plus 3S plus 2. Okay, now that is further equal to S plus 1. Again, denominator is factorized, and that is S plus 1, S plus 2. Here, what do you observe is? S plus 1 gets cancelled. Okay, and the transfer function is 1 upon S plus 2. There is a pole 0 cancellation, dear. There is a pole 0 cancellation. And in the CCF model, whenever there is a pole 0 cancellation, system will always be unobservable. In the CCF model, whenever there is the pole 0 cancellation, the system is always unobservable. Always unobservable. If you want, you again check with the Kalman's test. What is the CA matrix? C is 1, 1. A matrix is 0, 1, minus 2, minus 3. Multiply kiya to 1. This is 1. Then 1 and minus 3, minus 2. Okay. So what is the V matrix? That's going to be CCA. That is C, which is 1, 1. And CA is 1, minus 2. Okay. Oh, sorry, ulta likh diya maine. What is the CA matrix? हाँ, correct, 1, 1. And CA matrix, I think ये wrong आया है, 0. This is minus 2 actually. Sorry, a typo error here. 0, and this is perfect, minus 2. This is 1 and minus 3. Yeah, that is also minus 2. So this is minus 2, minus 2. Okay, what is the determinant of V? What is the determinant of V? Determinant of V, okay, minus 2, minus minus 2, 0, and hence the system is unobservable. Same thing Kalman's will tell you. Same things Kalman will tell you. Okay, so that is why now if I go to the previous, I stopped here. Na? In the previous case, by the Kalman's, we found system is observable. The system is observable. Is there any pole 0 cancellation here? Okay, Is there any pole zero cancellation here? Look into it. There is no zero only, na? Then how can it cancel with the pole? So definitely there is no pole zero cancellation. Okay, that is why the system is observable. That is why the system is observable. Okay. And as per the Kalman's also, we proved that it is observable. Okay. So we can, summarize this. Okay. When the pole zero cancelled, the system turned out to be unobservable. Okay. So please remember, okay, whenever you have a CCF model, okay, the first point to be noted is it is always controllable. Please don't check the controllability. Second point is कि if there is no pole zero cancellation, okay, then the system will be observable also. Okay, but if pole zero cancels, then the system is not observable. Then the system is not observable. Then the system is not observable. Okay, unobservable. That is a technique. Similar things can be repeated for OCF also. Okay, OCF also. Coming to that also, Venkat. Not directly, but indirectly, arrangement of the matrices affects. See, stability primarily depends on the poles, Hari. Okay, and poles of the system are equal to, in the state space model, they are equal to the eigenvalues of the matrix A. They are equal to the eigenvalues of the matrix A. So primarily stability depends directly only on the matrix A. Only on the matrix A. Okay? Yeah. So look into it. Third order, where factorization may be a difficulty. Look into it. Third order. Whether the system is observable and controllable. Have a look into this question, please. Just let me know quickly. Look into it, guys, whether it is CCF first of all. Okay, look into it. First, last row minus A0, minus A1, minus A2. Other than that, first column zeros and then I matrix. Yes, it is the perfect CCF model. Okay, plus 0, 0, BU, Y equal to C0, C1, C2, X. CCF hai. So hence controllable. Okay, and then this is known as minus A0, minus A1, minus A2. This is B. This is C0, C1, C2. So what is the transfer function? What is the transfer function? B, which is equal to 2. Okay, only C0 is there actually. Only C0 is 1, other are 0. Okay, so 0 into S square, 0 into S plus C0, C0 is 1 divided by S cube, ये third है. Okay, so what is A0? Minus A0 is minus 3. Okay, so A0 opposite sign के साथ चलेंगे 3 and that is a constant term. So let me write reverse. Then 4S and then 5S square and then S cube. That is Y by U. Okay, so basically what is Y by U? So numerator is only 2. Okay, 0, 0, 1. Okay. Two upon S cube plus 5S square plus 4S plus 3. Now tell me, dear, tell me, is there any pole zero cancellation? Here you don't need to factorize. You need to factorize if there is a 0, then you need to check whether it cancels with pole. But there is no 0, so it cannot cancel with the pole. It cannot cancel with a pole. So definitely there is no pole zero cancellation. Okay, and hence the system is observable also. So answer is option number A. It is controllable as well as observable. Now this third order system, same question, if you try to solve by the Kalman's test, 100% it is going to be much lengthy, especially for third order. Okay, A square B. You have to go up to A square B. Okay, and remember it's going to be 3 cross 3 multiplications. Okay, a square of a 3 cross 3, it's going to be time taking if you do by Kalman's. Okay, answer will be the same. Answer will be the same. Chalo, next question dekhte hain. Okay, again third order, next question. Tell me dear answer for this. Tell me. Consider the state space model given below. Okay, again look into this dear. Again look into the arrangement. Minus A0, minus A1, minus A2. That is the last row. Okay, then first column, zeros. Other than that, identity matrix. Okay, plus 0, 0, B, U. Y equal to C0, C1, C2. Perfect. It is CCF again. CCM hai, CCF hai, the system is controllable, no doubt. Okay, what about observability? For observability, okay, I can again go for Kalman's, but I'm telling you Kalman's for third order will be lengthy. So let's take the pole zero technique that I'm telling you. So Y by U agar check karenge, to B is just 1. Okay, then C2. C0 is the constant term, na? Agar C0 se start karenge, that is 2. Then reverse mein chalenge 1 into S. Okay, plus 0 into S square. Divided by again denominator mein the common term, the constant term is 24. Okay, then go reverse 26 S, then next is 9 S square and then S cube. Okay, so what is Y by U actually? Let us check here. Yeah, इसको यहीं complete कर देते हैं. Where is Y by U? This is looking like S plus 2 upon. Can it be factorized? You have S plus 2 upon S cube plus 9S square plus 26S plus 24. Now here you might be stuck. Okay. Here you might be stuck. क्या करेंगे? Okay, because you don't have scientific calculators also in the exam. You have virtual scientific calculator, but in that cubic equation is not there. Okay, so what I know is how to deal now. Okay, 0 is at minus 2. Do you need all the poles? No, you don't need all the poles. I don't need all the factors. I only need to know whether minus 2 is also a pole. Okay, so now what you're supposed to do is check S equal to minus 2 in the denominator. Check this in the denominator. Okay, so minus 2 ka cube, 9 into minus 2 ka square, plus 26 into minus 2, plus 24. Okay, you check this. Minus 8, plus 36, minus 52, plus 24. Ye ho gaya 60 minus 60, turning out to be 0. That means minus 2, when you substitute in the denominator turns out to be 0, and that is why that is a minus 2 is a pole also. Minus 2 is also a pole. Minus 2 is also a pole. Okay, that means there is pole 0 cancellation. I can say that. I didn't say that. Yes, but I think for most of the cases this is simple, Ajay. Okay. ठीक है, तो आ जाते हैं. I can say that S equal to minus 2 is also a pole. That means S plus 2 will be a factor into some other factors which I am not interested. Okay, which I am not interested. But what I am looking here is S plus 2 cancelled, pole 0 cancels, and this system will be not observable, unobservable. So it is option number B. It is controllable but not observable. It is controllable but not observable. Okay, controllable but not observable. ठीक है. Now next technique to be learned, Gilbert's test की तरफ जाते हैं. But before that guys, quick update that this 30 and 31st, that is tomorrow, Saturday and then Sunday, okay, BYJU'S exam prep brings you the next national scholarship test for the GATE exam, in which you appear and based on your performance you can get as much as up to 90% scholarship on the GATE preparation programs, right? And accordingly, you know, you can enroll and start your journey for the GATE preparation. And also guys, are you feeling stressed? Okay, what are the tips to handle the stress during the GATE preparation, because lots of students handle it. Okay, the tips to handle stress during the GATE preparation, a free live interactive workshop by all your favorite Richa ma'am on the BYJU'S exam prep app, coming up this Wednesday, 7:30 p.m. You can register now on the app so that you get the complete updates about the workshop. So if you don't have the BYJU'S exam prep app, you can just go to the description of this video. There will be a link to download the app. You can download from there very easily. Okay, and also guys, okay, the full-fledged courses for GATE and engineering services 2025 and also 2026 available on the app, okay, in English and Hindi, both formats, so you can choose language of your comfort. And there in the classes you get, in these courses you get live classes, recorded lecture facility, study material, mock test, practice quizzes, everything to get you exam ready. So for any other updates about these courses, maybe fees updates or timings or any other queries you have, you can contact 924-133-666 and get your queries rectified. And now let's go into the review. Again the review zone, थोड़ा सा revision करेंगे. The next special model is the DCF. See, I have revised CCF and OCF for you. Okay, all right, good to know Venkat, good to know Manasvi. Okay, देखिए, now the next thing that we need to revise here is, okay, is the DCF model. Okay, y by u equal to b, c2s square plus c1s plus c naught upon sq plus a2s square plus a1s plus a naught. Okay, so in the DCF model what we do, okay, whatever transfer function is given, okay, whatever transfer function we given, first denominator, see I am starting with third order, so we factorize the denominator. And suppose it turns out to be s plus p1, s plus p2, s plus p3, okay, where p1, p2, p3 should be unique. Okay, and then, you know, then we split into partial fraction and we write it as k1 upon s plus p1, k2 upon s plus p2, k3 upon s plus p3. Okay, then the model that turns out is, okay, x dot is ax plus bu, where a will be a diagonal matrix. Okay, remember p1, p2, p3, they are all distinct. They should not be same. Okay, so here the matrix A that you get, what type of matrix you get here? Very clearly what you're getting is a diagonal matrix. Elements other than the diagonal are 0. Okay, so you have a diagonal matrix. Okay, that is how this form is known as diagonal canonical form. Okay, you get a diagonal matrix. Okay, but with non-repeated diagonal elements, non-repeated poles, ऐसा भी बोल सकते हैं. Okay, p1, p2, p3 are the distinct poles. The poles should not be repeated. Okay, so you get a diagonal matrix whose diagonal elements are not repeated. Okay, all of them should be unique, minus p1, minus p2, minus p3, plus bu, where b is L1, M1, N1. Okay, and y equal to L2, M2, N2. Okay, where, how do we calculate? See, here again my interest is not teaching state space model, but just basic revision is required. Okay, so L1 into L2. Okay, how do you decide this elements Lmn? L1 into L2 should be equal to K1. Okay, K1 is the first partial fraction coefficient. M1 into M2 should be K2. Similarly, third, N1, N2 should be equal to the K3. Okay, now next case. Okay, next case, again suppose you have a third order, but suppose, okay, P1, P2, okay, third order you will have 3 roots, third order you will have 3 poles, out of which P1, P2 is same. Okay, sorry, P2 the different, I am sorry, but out of which P1 is repeated. Okay, and P2 is unique. That comes only once. Okay, so when you have repeated pole case, once again I first split this into the partial fraction I write it as k1 upon s plus p1 whole square plus k2 upon s plus p1 plus k3 upon s plus p2. Okay, please note that first term is s plus p1 square, then s plus p1. Pehle second order, then s plus p1 and then s plus p2 term. Okay, then the model that turns up is x dot is equal to ax. Okay, where A matrix is a upper triangular matrix. Okay, containing the diagonal numbers minus p1, minus p1, minus p2, and above this repeated pole there is the minus 1. Okay, and lower elements are 0. That is why I am calling it as upper triangular matrix. Okay, so in this model, which is known as the JCF model, Jordan canonical form, okay, you get an upper triangular matrix. Okay, upper triangular matrix with repeated diagonal elements. At least one diagonal element is repeated, minus p1, minus p1. With repeated diagonal elements. Okay, plus BU. What is B? 0, B11, 0, 1, 1, and Y equal to K1, K2, K3. What is K1, K2, K3 here? Directly the partial fraction numbers, partial fraction coefficient will come. K1, K2, K3x. That is the JCF form. Okay, now let's come back to controllability, observability. This is what I wanted to have a quick revision. More about these forms you can study later in in my other classes of state space model. Okay, now let us come to the Gilbert's test of controllability and observability, but only for normal forms. There are two normal forms. Normal forms are DCF and JCF. Okay, so Gilbert's test is not for any other form. Like Kalman's test can be applied to any control system, but Gilbert's test can only be applied to the DCF or the JCF form. तो पहले DCF वाला study कर लेते हैं. Let us study for DCF. Okay, the controllability test. Entire row of B matrix. I'll explain you with example and then it becomes very simple. See guys, you can from here get 2 marks question. You can solve in 10 seconds. So powerful the Gilbert's test is. Okay, controllability test. Entire row of B matrix that corresponds to distinct eigenvalues should not have all 0 elements. Example se samjhenge. Then we will go to the observability test. Okay, suppose this is a state space model given to you. Okay, and I need to check the controllability and observability. ध्यान देना यहाँ पे. Okay, ध्यान देना. Okay, first of all, look into the matrix A. Look into the matrix A. Is it a diagonal matrix? Yes, only diagonal numbers are there. Elements other than the diagonal are perfectly 0. So yes, this is a diagonal matrix. So by diagonal matrix, should I say it is DCF? No, you have to check that it should be diagonal matrix with non-repeated eigenvalues. 1, 2, 3, all are distinct. Okay, all diagonal elements are distinct. So it is a diagonal matrix with non-repeated diagonal elements. So hence it is DCF. Hence it is DCF. And if it is DCF, I will go for Gilbert's. Okay, let us first learn the controllability. ये separate slide में समझ लेते हैं. Let us first learn controllability and then I will take the observability. ठीक है? क्या बोला है? Entire row of B matrix that corresponds to distinct eigenvalues should not have all 0 element. Okay, so row of B matrix corresponding to distinct eigenvalues. So dear, there are the 3 eigenvalues here. -1, -2, -3. Okay, 3 diagonal elements represent the 3 eigenvalues here because it is a diagonal matrix. I think some correction in video. Now it is okay. Okay, look into the first diagonal element. Yeah, look into the first eigenvalue. Okay, corresponding to this first eigenvalue, go to the first row of B. Corresponding to first eigenvalue, go to the first row of B, and whether it is a 0 or non-zero row. Okay, it is definitely a non-zero row. Let me call it as NZR. Let me call it as NZR. NZR से मेरा मतलब है non-zero row. Okay, then for second eigenvalue, I will go to the second row of B. That is also NZR. For third eigenvalue, I will go to the third row of B, and that is row of 0. Here you have one element, but ultimately that one element 0 means entire row is 0, na? Entire row is 0. Here you get a row of 0. ROZ I will write in short. That is known as row of 0. Okay. What I told you. Okay, entire row of B matrix corresponding to distinct eigenvalue should not have all 0 elements, but I got one row of B. I have got one row of B, okay, which contains all zeros, which is a row of 0. Okay, even if there is one row which is row of 0, okay, then the system is, because of this row of 0, you will say that the system is not controllable. the system is not controllable. The system is not controllable. So simple it is. So simple it is. ठीक है. Then what about observability? चलो observability भी यहीं पे बता देते हैं. Observability भी यहीं पे बता देते हैं. For observability, let's read the test first. Okay. Entire column of C matrix. Entire column of C matrix that corresponds to distinct eigenvalues should not have all 0 elements. Okay, now we need to go to the columns of C matrix corresponding to distinct eigenvalues. So here a first eigenvalue corresponding to first eigenvalue, go to the first column of C. Okay, is it 0? No, it is non-zero column. Like NZR, I call NZC. Corresponding to second distinct eigenvalue, you go to the second column of C, and is this 0? Yes, it is full of 0, and I call it as COZ. Okay, like ROZ, this is COZ, and even if you get a single COZ, okay, this concludes that the system is unobservable. This concludes that the system is unobservable. You should have all columns which are non-zero. Okay, chalo, by chance let me check third, but answer is anyways concluded. But okay, if I take the third eigenvalue, I will go to the third column of C, and that is NZC. Correct. So problem is the second column, and the system is uncontrollable. So the answer is not controllable, not observable. Option number C. It is uncontrollable as well as unobservable. Achha, here advantage is you can also say which state. As I told you, even if a single state variable is not controlled, then the entire system becomes uncontrollable. So what I can say, the system is uncontrollable because of the third state. Dekho, kis state, okay, kis element ki wajah se 0 aaya hai? That is the third element. That is the third element. You can here say that actually, you can here say that here, the state x3 is uncontrollable. See, they are not asking, but just you should know. Out of the 3 state variables, the state x3 is uncontrollable. Now, the system is unobservable because of the second column. Okay, here you can mention that the state x2, the second state actually is unobservable. Mostly they don't ask this, but still you should know. The state x2 is unobservable. Clear? The state x2 is unobservable. The state x2 is unobservable. ठीक है जी, डन है, हो गया. Yes, Vikram, definitely. चलो डन है. अच्छा, this is repeated, forget. So, dear, if I want to generalize, okay, a 3x3, okay, a 3x3 controllable as well as observable DCF model, how it will look like? Okay, a 3x3 controllable and observable DCF model, how it will look like? It will look like x dot is equal to DCF hai to diagonal matrix with non-repeated diagonal elements. So minus P1, minus P2, minus P3, all are distinct. Rest are 0. X dot is AX plus. See dear, why controllability failed? Why controllability failed? Because you got one row of 0. Here you got this 0. If this was also non-zero, the first two were non-zero rows. If this row also was non-zero, then the system would have been controllable. So if you want a controllable case, okay, you should have non-zero row here, you should have non-zero row here, you should have non-zero row here. That's it. Okay, if you get this by chance, you can just look into the numbers and you can say the system is controllable. Similarly, output equation pe aayenge, y equal to the cx. Okay, the system failed observability because the second column was 0. If this was also non-zero, rest two were clear, then the system would have been observable also. Then the system would have been observable also. So here also, in first column also I want non-zero, second also I want non-zero, third also I want non-zero. If this is satisfied, then the system is observable also. Okay, so whatever is satisfied, if only those three is satisfied, then controllable, maybe it is not observable. Okay, yeah, like the previous example, not controllable also, not observable also. So I have generalized this for you. I have generalized this for you. ठीक है? अच्छा जी, अब देखो. Similarly, can we also write 2x2 controllable and observable canonical form? 2 क्रॉस 2 कंट्रोलेबल एंड ऑब्जर्वेबल DCF फॉर्म, ये लिख लेते हैं x डॉट 2 क्रॉस 2 मैट्रिक्स, ओके, diagonal matrix having different distinct eigenvalues minus p1 minus p2, okay. So here also for it to be controllable, okay, here there will be only two elements, two rows in B, na? Two rows in B, both should be non-zero. Similarly, two columns in C, both should be non-zero. Okay. Then the system, this ensures controllability, this ensures observability. Okay. This ensures C matrix observability and this B matrix ensures controllability. ठीक है? चलो, now let me tell you something here. Let me see where is that question. Here it is in sequence only. Have a look into it. GATE 2016 ISC Bangalore 2 marks question. GATE 16 ISC Bangalore 2 mark question. Okay, you need to comment on controllability and observability. You are given d by dt of x1. Let me write this. Okay, let me write this. D by dt of x1 means x1 dot. Derivative is represented by dot, na? Okay, is equal to how much? Is minus 2x1 plus 3u. Minus 2x1 plus 3u, and d by dt of x2, that is x2 dot. Okay, that is x2 dot is how much? चलो पूरे क्वेश्चन को यहीं खत्म करेंगे. Okay, let me write it like this. Okay, what is x1 dot? Okay, minus 2x1 plus 3u, and second equation से get x2 dot. So dear, what is x2 dot? Okay, minus x2 on the other side plus u. Okay, plus u. Okay, so I can write down here x1 dot x2 dot directly matrix form is equal to ax plus bu. So what are the coefficients? First row minus 2x1, there is no x2. Second row only x2 with minus 1, there is no x1. Input दोनों में present है. First it is 3u, second it is 1 into u. Okay, now output equation. Output is y equal to x1. Okay, output को C बोला है, let us call it as y only. Y equal to x1. Let us call y equal to x1. Okay, so y is equal to x1. So if you want to write down coefficient, x1 is 1, x2 is 0. Is it DCF? Is it DCF? I think perfect. This matrix tells you कि ये DCF है. Diagonal matrix with distinct diagonal elements. With distinct diagonal elements confirms DCF. If it is DCF, I will look into the elements of B. 3, 1, both are non-zero. Non-zero, non-zero. The system is controllable. No Kalman's test required. Now I'll look into the C matrix. Okay, yeah. Both should be non-zero, but one of them is 0. So the system is not observable. It is controllable but not observable. It is controllable but not observable. Answer is D. I get 2 marks easily. I can get the 2 marks easily. Okay. Similarly, let us study the Gilbert's technique for JCF also. Okay, the Gilbert's technique for JCF also. Okay, what does it say? What does it say? Number 1, controllability test. Entire row of B matrix that corresponds to last row of a Jordan block. अब देखो, what is a Jordan block? Let me explain you that first. पहले question लेते हैं. Okay, then first let me explain you Jordan block and then we will come to the test. Have a look into this. Okay, consider the state space model given below. Okay, first of all, look into it. Whether it is JCF, look into the matrix. Is it upper triangular matrix? Yes, elements below the diagonal are 0. It is upper triangular. It is upper triangular matrix. But the condition is it should have repeated eigenvalues, repeated diagonal elements. Okay, -3, yes, at least one of them is repeated. So yes, there is repetition. So upper triangular matrix with repeated diagonal elements, that confirms JCF. Only upper triangular से कुछ नहीं होगा, but there should be some repeated diagonal elements. Okay, this confirms JCF model. Okay, it is JCF. Okay, it is JCF. Okay, yes, Vikram. Chalo, now let's come here. Okay, now it is JCF. Okay, so now first, what is the Jordan block? First, what is the Jordan block? See, there are three diagonal elements. There are three eigenvalues, -3, and 1. Okay, -3 जो है that is repeated. Okay, कितनी बार आया वो? 2 times. जो -3 है that is coming how many times? 2 times. That is coming how many times? 2 times. I will pack it in a 2x2 Jordan block. Because it is coming 2 times, I will pack it in 2x2 Jordan block. I will pack it in 2x2 Jordan block. What is that 2x2 Jordan block? This is the one. I call it as J1. Okay. One Jordan block contains this eigenvalue -3. It is repeated 2 times and that is why 2x2 aa raha hai. Okay. Now, next 1. Okay, 1 ये distinct है. This is not repeated. मतलब how many times it is coming? It is coming distinct means it is coming only 1 time. Okay, because it is coming only 1 time, it will be packed in a 1x1 Jordan block. It will be packed in a 1x1 Jordan block. Okay, ये रहा. This is going to be packed in this 1x1 Jordan block. Okay, this is J2. This is 1x1 Jordan block and that is J2. Clear? Okay, that is the J2, 1x1 Jordan block and that is known as J2. Clear? Okay, chalo, now let's move ahead. Okay, now let's move ahead. Test. Entire row of B matrix that corresponds to last row of a Jordan block should not have all 0 elements. So let's check here. ये तो block explain किया. Now let's come here. Let me again draw those two blocks. This is the J1. This is J2. What I told you, entire row of B matrix that corresponds to last row of a Jordan block. So this is the Jordan block J1 and this is the last row of J1. Okay, but you have to see, dear, listen to me carefully. The last row of J1 is overall which row? Overall from the top it is second row. Overall from the top it is second row. So you will go to the second row of B. And it is a row of, अरे यार यहाँ नहीं, let me write it in the separate page. ये रहा. Okay, this is the last row of the Jordan block J1. Overall that is the row number 2. Okay, and because it is the row number 2, I will go to the second row of B and that is row of 0. That is row of 0. And if it is row of 0, uncontrollable. Okay. If this was non-zero row, then we will go to the J2. वो भी समझ लेते हैं. Although answer is done uncontrollable, but let me make you explain the next case also. Okay, so this is the next J2. Last row of J2. This J2 has only one row. The last row is this only. But the last row of J2 is overall 1, 2, 3. Overall third row, na? Overall third row. Okay, so you will go to the third row of B. And what is the third row of B? That is NZR. That is NZR. That is NZR. Clear? So that is not a problem. Okay, but the system is uncontrollable because of this row of 0. That means, dear, before I go to observability, okay, if I want to write down a 3x3 controllable and observable, 3x3 controllable and observable JCF model. ठीक है? JCF तो upper triangular matrix but with repetition -P1 then -P2 upper triangular है -P1 के ऊपर repetition के ऊपर 1 आता है. Okay, x dot is AX plus BU. Now what should be the B matrix? Okay, then we will talk about C matrix later on. Okay, what I needed here, this should also be non-zero row, this should also be non-zero row. Okay, here what you should have NZR, here also what you should have NZR, here it could be anything. Don't care, here it could be anything. ठीक है, थोड़ा सा और साफ से लिख देंगे. Here actually it could be anything. That's not going to affect the answer. But if these two are non-zero, na, then you can call the system to be controllable. Okay? Then what about observability? Observability, entire column of C matrix corresponding to first row of Jordan block, should not have all 0 elements. Chalo. So let's come here. These are 2 Jordan blocks. Okay, now J1, first row of Jordan block to be checked, and first row of J1 is overall which row? Overall also first row, overall top mein hi hai, and corresponding to first row you will go to the first column of C. And check whether it is 0 or non-zero. It is a non-zero column. Good. It is a non-zero column. Good. Okay, no problem. Then J2. Okay, again I will check the first row of J2. Corresponding to the first row of J2, I will go to corresponding to the first row of J2. Acha, first row of J2 is overall which row? Again you check. This is the first row of J2, but overall 1, 2, 3. Overall this is third row. So I will go to the third column of C. Okay, I will go to the third column of C, and here also it is non-zero. Okay, so both are non-zero. Okay, so system is observable. The given system is observable, but it was not controllable. Answer hai, it is not controllable but observable. Answer is B. ठीक है? Not controllable and observable. Yes, answer B. So now, what is the generalization for JCF observability? Okay, JCF. Okay, we come to the first column, we come to the third column. We are not interested to the second column. So first and third, okay, should be non-zero. First and third should be non-zero column. So let me write down here. This should be a non-zero column. This should be a non-zero column, and in between here, you can have anything. Okay, if this is satisfied, then the system is observable. Finish. Now see how you can score 2 marks easily. 2 marks gate question easily. Easily means very easily, actually, very quickly. That is very easy and very quick. Tell me, dear. Hanji. See, 2 marks, and very quickly options are coming up because this is without calculation question. See, first of all, look into it. Upper triangular hai? Yes. Upper triangular with repeated? Yes, there is a repetition also. So first of all, you have to confirm JCF. Okay, and if it is JCF, okay, then I have told you the standard result. Okay, this is non-zero, but ye fail ho gaya. Because of this, system is uncontrollable. What we saw, the second and third, both should be non-zero rows. Okay, second and third. And similarly for observability, first and third column should be non-zero. Okay, first non-zero, third non-zero, ye kuch bhi ho, doesn't matter. Okay, the system will be, because of these two, the system is observable. That's it. Not controllable and observable. It is just observing. Okay, very easy to get 2 marks. If you solve this by Kalman's, very lengthy. Easily 2-3 minutes minimum, even if you are fast in calculation. Because 3 cross 3, A, B, A square, B. Right? Then observability, C, A square. Easily 2-3 minutes, even if you do fast calculation. But this is maybe just reading the question and solving 20-30 seconds total. Very important. Acha, if it is 2 cross 2, dear, ये तो मैंने 3 cross 3 बना दिया. Let me make 2 cross 2 also. 2 cross 2, controllable and observable JCF model. Let me summarize for 2 cross 2 also, dear, how it should be. Okay, but first of all, JCF will have upper triangular matrix with repetition, where 2 cross 2 means only 2 eigenvalues. Repetition is also required. So minus P1, there will be no P2 term here. Okay, because I can have only 2 diagonal elements and there should be repetition also. So both are minus P1. Above repeated likha, upar 1, below 0. So what should be the condition here? Let's understand. So basically, here you have only one Jordan block. Okay, P1 is repeated 2 times, so it will be blocked in a 2 cross 2 Jordan block. Okay, Then for controllability, I go to the last row of Jordan block, and corresponding to last row, that is overall second row, this element here should be non-zero. Okay, so let me write down the conclusion. This should be NZR. यहाँ पे कुछ भी आ सकता है. Similarly, again I take the Jordan block and I take the first row of Jordan block and I go to the first column, because first row is overall the first row also. So corresponding to the overall first row, I will go to the first column of C, and that first column of C should be non-zero. Okay, here it could be anything. Here also anything. Okay, so if this is satisfied, controllability will be there. Okay, and if this is satisfied, observability will be there. Observability will be there. ठीक है? ठीक है? Now, some questions which may confuse you and take you towards wrong direction. Have a look into it. Which method to apply here? Which method to be applied here? Consider the system d by dt is equal to ax plus bu. Okay, where a is 1, 0, 0, 1. What model it is? Plus tell me. First tell me please, what model is it? Please tell me what model is it? What model is it? What model is it? Tell me, dear. Is it DCF? हो गया ना mistake. Is it DCF? It is a diagonal matrix. Okay, and you think it is DCF. But it is a diagonal matrix with repeated poles. With repeated diagonal elements. How it can be DCF? I told you very clearly, DCF means diagonal elements with non-repeated diagonal elements. And then it is not JCF also, dear. JCF to upper triangular मांगता है. Okay. So dear, tricks are good, but always precaution. Basics गलत नहीं होना चाहिए. Here you got the basics wrong. Identifying the form was wrong. Okay. ठीक है. So it is neither DCF nor JCF. So what to do? Then you are left with no choice. You have to go by Kalman's test. Then go back to the basics ना जहाँ से start किया था, Kalman's test. Okay. Homework. Kalman's test, dear, we have understood na. So we are not solving right now. It is homework for you. I just want to show you the variety. Okay. Next question. Look into it now. Okay. Look into this matrix A now. Okay. Now upper triangular matrix. Definitely it is not diagonal matrix, so DCF to ruled out. DCF ruled out. This one is upper triangular 100%, but is it JCF? Upper triangular gives the temptation that the question may be JCF. The question may be JCF, but is it a Jordan canonical form? It is upper triangular but with non-repetition. No. Again, फंस गए आप लोग. It is not JCF. Upper triangular, okay, but non-repeated आया. But non-repeated eigenvalues या non-repeated diagonal elements. Non-repeated diagonal elements. So again, okay, it is neither DCF nor JCF, nothing. Getting? It is again neither of them. Okay, so if it is neither of them, then you will go to the Kalman's test, and Kalman's test solved a lot of number of times. I am giving you homework. So 2 homeworks are there for tonight. Okay. But both, very importantly, I wanted to discuss, at least I wanted to show you the question, because they are the possibility where you commit the mistakes, and I was looking that you are committing mistake. Be careful. Be careful. These tricks, this Gilbert's test is going to make your life simple. You have seen how 2-mark question of gate I've shown you within seconds. But where to apply Gilbert's? Only on the normal forms. That is either DCF or JCF. Okay, but not on any other. So DCF, I repeat and then I close the session. DCF, diagonal matrix with non-repeated diagonal elements. JCF, upper triangular, but repetition. At least one element should be repeated. Okay, so be very clear what is DCF, what is JCF, and here that's it for today's session from my side. Chalo, let's keep a simple password for today. Kya password rakh dein aaj ka? Ye lijiye. The password for today is DCF. Okay, you will get the PDF in my Telegram group and with the password protection, and the password is going to be DCF, diagonal canonical form. In short, only DCF. Everything in short, that is DCF. All right, guys. So 30th of December is coming tomorrow, Saturday, and you have the next All India Open Mega Mock Test. Okay, and that's going to be a full-length mock test this time. Okay, 30th of December, I know it's not much visible here, but let me tell you. Okay, the test starting on this 30th of December is a full-length mock test exactly as per the GET pattern. And because these are All India Open Mega Mocks, these are free on the BYJU'S exam prep app. Okay, so thousands of students, aspirants are appearing, so you should also appear and try to see now, like when 1 month left for the examination almost, where do you stand, where is your preparation, okay, and how much you need to improve. Okay, so you can attempt it. This MMC is going to be live from 30th December to 5th January, any date at any time at your convenience, you can appear into it. Right, that's it dear from my side. Bye bye, thank you, good night, stay safe. Okay, again we have a healthy almost more than 1.5 hour of session. Bye bye, see you in the next session. Till that time, take care of yourself and keep preparing hard.